Firstly, I would like to offer our apologies for not being there today in person to present this to you in my name and in the name of our team. But it is a pleasure to be able to talk to you about classifying power quality disturbances in noisy conditions using machine learning. We are a team of 4, I will mention just briefly, including me, Bojana Velichovska, and my colleagues Maria Markovska, Christian Gjoreski, and Dimitar Pashkovski. We are from the Faculty of Electrical Engineering and Information Technologies based in Skopje.
Okay, you have 10 minutes. Are you familiar with these time constraints?
Yes, I'm familiar with the time constraints, and I will do my best in order to maintain them.
Great.
Okay, so different power disturbances surge daily in the power grid, and therefore it is important to make their detection and classification in order to preserve the customary satisfaction and make it the best grid for the customers. So for that, we decided to do an analysis on previous works, including this type of problem, so disturbances in noisy conditions. The previous researchers which dealt with classifying power quality disturbances did feature extractions mostly based with wavelet transform and discrete wavelet transform. I seem to be, okay, so here we are. So the feature extraction methods such as Fourier transform, wavelet transform, and discrete wavelet transform are present, and after the features have been extracted with these methods, those features that were obtained were given to a classification method as a time series analysis or maybe SVMs, decision trees, and RFs. So taking into consideration these previous researches, we decided to try and do something that has not been done before. So most of the previous work shows classification of only 11 classes, whereas we analyzed 21 classes. And every work before has been done with fixed noise influence, meaning that we have the constant noise in every single class throughout the entirety of the data set. We, on the other hand, do something slightly different. So what happens with our data set is that we now have 21 different types of PQ disturbances or classes. Each of those classes are either accompanied with 20 decibel, 30 decibel, 40 decibel, or 50 decibel white Gaussian noise. But what is new and we didn't encounter in previous research is the combination of those, meaning that we have one data set in which all the samples are either with 20, 30, 40, or 50 decibel noise, but it has not been labeled in the exactness of the noise. So it's a mixed noise in one data set. Each of those 5 data sets that I just mentioned were with train and test samples, train and test data sets with 1,000 samples per class, meaning that the train and the test data set consisted of 21,000 samples each. We began with extracting features with the TS-Fresh library for automatic extraction in time series. The TS-Fresh library gave us a significant number of features, which meant that in order to make the model more easily trainable, and in order to make the training method a faster one, we decided to reduce the number of features which TS-Fresh gave us. So we did a feature selection module in order to do that, in order to reduce the computational efficiency of our models. The feature selection, as such, occurred with calculating the mutual information between each extracted feature which we received from the TS-Fresh library and the class. So the mutual information gives us an idea of how one feature influences the result of the classification. We left at the end 300 features, which means that we had the 300 most relevant features to the class. And then we calculated Pearson correlation coefficient for each of the two features, meaning that we had pairs of features tested. If those pairs of features gave a correlation coefficient that was higher than a certain threshold, we had the coefficient with the feature with the lower mutual information removed from the pair, and the other one just remained for the final set of features. As to the machine learning algorithms, we decided to test some machine learning algorithms which have already been done in previous researches, such as decision tree and random forest, both by researchers from other universities and some of our authors or co-authors of this paper. And also there was the addition of XGBoost, which we wanted to test since it has proven to be something of a great classifier, but we did not manage to encounter it in any previous research material on this concrete topic. Our evaluation setup, or our models, were trained with the 5 above algorithms. For each of those algorithms, we performed the training on the 4 different subsets of features we extracted. So all the extracted features which TS Fresh provided, all the selected features from our feature selection module, and then those selected features we divided into 2 groups, features which were in the time domain and features which were in the frequency domain. These models, these feature sets were used on each of the training data sets, so on 20 decibel noise training data set, on 30, on 40, 50, and on the combined data set of noise where we had 20, 30, 40, and 50 in one data set. The results showed that XGBoost globally on every single data set with every set of extracted, selected, and other features, with every classifier we had, shows the best results, the highest accuracies of the entirety in general. It's not a particular case everywhere, as we can see in this table. This result table is shown where we have a data set with 20 decibels of white Gaussian noise, and we can see that with most of the feature sets, which are given as columns, we have the best results with XGBoost, but with the extracted features data set, the classifier, nearest neighbors, and gradient boosting do just a slightly better job at classifying the disturbance. Here we have the 30 decibel white Gaussian noise. Again, XGBoost in most of the cases proves to be the best classifier in general, as is also visible in the 40 decibel Gaussian noise data set. So I'm just going to show you, this is the 50 decibel table, where again XGBoost with nearest neighbors is fighting for the first place of all the extracted features, whereas for every other feature set, XGBoost is the best. What I'm going to focus on mostly is the 20 to 50 decibel white Gaussian noise data set, because this is something that was not that we did not encounter in previous works. So again, this data set consists of different denoised signals, so each signal can have a different amount of noise. We decided to try this because, of course, in the grid the noise is not constant all the time, so we wanted to see if we can do something that is invariant to the noise. So in this case, again, XGBoost shows the best performance, but what is very important to note is that we have, once we divide the features in time domain and frequency domain features, we have a significant drop of the accuracy when it comes to frequency domain features compared to the results which time domain features give us. So that is an issue we would like to address in our future work, along with some additional machine and deep learning method applications to the problem. So what I presented to you today is a machine learning method for classifying power quality disturbances in noisy conditions. We have analyzed the effect that the noise provides on the quality of classification, which in our case proved that we have models which are invariant to the noise because the results are quite similar in 20, 30, 40, and 50 decibels. The 50 decibel white Gaussian noise datasets. So we have something that can be used perhaps with a little bit more work in the real world. Thank you for your attention. I hope that I wasn't too slow on the presentation. Are there any questions?
Thank you.
Thank you.
Time for questions? Not a single one.
I have a question. Can you hear me?
Yes, I can hear you.
So maybe I missed something, but it's not entirely clear to me what was your data. So I mean, what was the thing from which you calculated the features? How
Okay,
was it
so
collected?
so our data is generated with MATLAB and is done by, so perhaps I didn't give too much detail on that because it's done by another member of the team. What I can tell you is that we have signals. So we have the timeline and values of the power signal which happens during that timeline. So we have a time series of the data itself.
So, but
They are
what
simulated in
what
MATLAB.
does this represent? I mean, is this voltage in a power grid, or what is it?
This is the, yes, this is voltage, right? It's voltage in the power grid. It's a power signal, yes.
But it is synthetic, if I understand correctly.
I'm sorry, is it what?
Is it altogether synthetic? Since you said
Yes.
it's generated in MATLAB?
It's generated in MATLAB with previously, I think it's a code borrowed from a previous research which has been already approved. So we're using that to generate the signals here.
Okay, thank you very much again. We ask you for a moment of attention, please. Okay. 2 minutes, Martin. Rock, will you come, please? Namely, this year we would have been looking for the best paper, and of course there is a €1,000 reward for the best paper. And, Rock and I will proclaim it. Okay, Rock, come in. And the winner is.
Maybe we will see what did we base our decision on.
Okay, now it's yours.
Maybe it's important to say that we wanted to present this award already last year, but we didn't have a really good methodology to decide which paper is the best. So this year we evaluated it according to 3 criteria. So the scientific excellence, the impact that the paper could have on the field, and also on the presentation. And the paper that we selected was selected unanimously. It had, among all the papers, really good scientific impact, excellence, and the thing that I liked the most about it is that the presentation was very good. Actually, this was a paper in Slovene, and one important thing that we often forget is to put attention on Slovenian terminology. I mean, this paper, it was really done well, and this is one additional benefit why this paper deserves the award. So, without further ado, okay, so the best paper award at the Slovenian Conference on Artificial Intelligence goes to the paper entitled Razvoj postopka teritorizacije govorcev z algoritmi strojnega učenja. The paper is written by by authors Marko Katrašnik, Juno Šlukan, Mitja Luštek, and Vitomir Štut. So I would like to invite the authors.
Slikavo. Kako se te zavodimo ovlasti, ne? Čestitam, 1, 2, 3, nego manjka.
Ja,
Smešek? Ok, 1000 evrov pa bo nekoč, ko si boste sami izplačali.
okay.
Thank you everybody, it was really a nice, really quality session. With this we conclude the session. Thank you very much. See you next year.